Let's analyze the workflow required for a prismatic part from scanning, now with a high-resolution scanner, through all the necessary processing in both the scanner's application and CAD software, in this case, Autodesk Fusion. I'll start with a simple object, a prismatic one. The object I'm trying to create is this one you can see here. It's an electronic component, part of a joystick with just one axis. However, as you can see, it's not ready to be scanned. It has many reflective surfaces, so we need to apply some treatment. In this case, I'll use that spray you're already familiar with. I can even show it to you. The spray I'll be applying is this one. I'm not sure if you can see it clearly, but yes, it's this one here. So, this is the first step, and I'll scan this using a higher resolution scanner because, as you can see, the part is quite small. We're talking about a part approximately 20 millimeters in size, maybe around that. With the part already sprayed, we'll begin the scanning process. We've prepared the scanner to start the scanning process. Let me show you. The tool we'll be using is this one. This is the scanner, by the way. Now, let's begin a new scan. The object is balanced with proper lighting and set with the correct exposure. I'll just adjust the object tracking so it can follow these red markers you see here. I'll also do another exposure check. I always like to verify that everything is correct, even though this scanner was recently updated. The update specifically focused on auto exposure. What's happening now is that the scanner is doing a 360-degree rotation. I'll capture about 450 to 500 frames, which I believe is sufficient for this object, and will allow it to appear fully, at least the visible faces. There are moments when it seems to lose alignment with the object, but it quickly regains it. The reason is simple. I'm scanning at a very low angle, almost parallel to the plane of the table. For this reason, this happens. Capturing 460 to 470 frames should suffice. Here we have our point cloud. I'll perform the fusion and increase the resolution to the absolute maximum. Still, values like 0.05 millimeters on this scanner can only be achieved with what they call a single shot, a single capture. But from my experience, even with continuous capture, this significantly improves the dimensional accuracy of the scan. Now, cleaning up the mesh, I'll try to find isolated or overlapping elements. Now we'll proceed to a new scan. For now, I need to adjust the object's position. Here we have the scanner's light, which is used for scanning. This 3D scanner uses this blue light. We'll rotate the part to capture the blind angle that wasn't previously visible, and then return to the software to start the capture. Once again, it's always a good idea to verify if the exposure is correct. In this case, it is. Also note the object's position in the bars on the right, which resemble a histogram, indicating that the object's position is excellent. This means the capture will likely be performed with high quality. Without a doubt, this scanner is an excellent tool for metrology because the precision achieved by a scanner of this class is impressive. For this type of part, not in terms of shape but size, especially small parts, I believe there's currently nothing that can compete at this price point. The capture is complete, generating a new point cloud. We'll create the fusion with the same properties. Notice there's an option to directly erase the markers, simplifying the process. The part is almost finalized, with no strange elements or additional objects. This process also removes some islands that may be detached from the main domain. Here, we are removing overlapping elements. At this stage, I'll align the two scans. This software rarely fails in alignment. It performs a very precise alignment, and it's uncommon for the alignment process to fail. With the alignment done, it creates a new point cloud, which is the result of merging the two captures. Here it is. We exit this stage and move on to the fusion process. This was the second capture. I like to compare the captures to understand where each element was recorded. Note that there are some faces with large holes that likely come from the second capture, while the first capture ended up gathering much more information. Eventually, the first capture alone would have been sufficient for the necessary measurements. However, since this is a tutorial, I prefer to show this situation as well because I find it relevant. In this step, we attempt to identify detached islands or overlapping points. Finally, we'll create the mesh with the maximum resolution. This will result in a somewhat large model. In this case, large means heavy. A model with a lot of information and a very dense mesh. I prefer to later improve and reduce the size of the elements in Fusion, which provides very interesting tools for this purpose, namely the possibility of creating a dynamic mesh where, in flat areas, it generates much more spaced and larger triangles, and in areas requiring more detail, it forces smaller triangles. And it's done. It took me much less than the estimated 5 minutes, and this is the final result. Now, all that's left is to export. I'll export in additional formats. This PLY format, I'm not sure why it appears, I think it's only for point clouds. I'll use the OBJ format, and the export process is complete. We'll now start processing the image in Fusion. I will import the model. I can do it directly into our environment. The model is on the computer, here it is. Meanwhile, I'll check the dimensions of the part. Let's switch to this mode. (21.97mm), approximately. Returning to Fusion, the part is now being prepared to be placed in the environment. I'll center it. In principle, nothing will happen. And indeed, nothing did. Okay, but before manipulating the part, I'll temporarily hide it and activate the origin system. In fact, I don't need to see this element at this stage as it would only get in the way. We'll place some lines that will help orient the model. I don't know if Fusion allows infinite lines like AutoCAD, but I'll create conventional lines. I prefer to convert the lines into construction lines because in fact that's essentially what they are. Let's reactivate the model, and before anything else, I'll measure the part from one point to another to verify the difference compared to the earlier measurement. We'll use the Inspect tool. I select this point, for instance, and approximately this point. 22.073mm. In other words, we have a very small tolerance, which demonstrates that this scanner has excellent accuracy. Now we'll do the alignment, and then perform another verification. For alignment, you can use the Move command. I'll try to use the icons instead of shortcut keys so you don't lose track of what I'm doing. This seems fine. I prefer to make one movement at a time, and each movement is then associated with the Move command. This step is definitely necessary. Let's position the element down here and notice how the lines start to make more sense. For example, when placing it here, it indicates -3 or -5 degrees. I was already thinking of -3, which seems reasonable. I rotate it to this area and use the move command again. Now, I perform a new rotation to adjust the model. Let's adjust the position where it is currently located. I know that larger adjustments would be excessive because it's set with increments of 5 degrees. Maybe here a -1 or minus 0.5 degrees? Yes, -0.5 seems to be the correct value. Here, it looks good to me. But can we fine-tune it further? Yes, it probably needs another adjustment of about half a degree. It's rotating negatively, so -0.5. I think it has improved significantly. A new rotation. And adjust as well. I'll just raise the model so this line aligns with the PCB's base. Now what's next? I want to perform a verification with more precision. Why? Because I'll click on this point and select the point on the opposite side. Now, we have 22.06 millimeters. We're achieving a very high level of accuracy here, around 1/10 of a millimeter. However, according to its specifications, this scanner can reach an accuracy of 0.05 millimeters. I remind you that this is an overlaid scan, meaning 2 scans combined. Potentially, a single scan could yield better results. I also remind you that this scanner allows maximum resolution in the single frame or snapshot mode. Basically, it performs a single capture, and in this mode, it achieves even better results. I think this can be considered a relatively reliable tool in terms of metrology because the results are quite good, at least for these types of applications. Now, let's move on to the mesh. We have the remesh process here. There are 2 aspects of this process that confuse me a bit. I typically use the reduce command, but remesh allows for mesh adjustments. Practically speaking, it rebuilds the mesh. What I usually do is use the adaptive mesh feature. What this does is make the mesh denser in areas that require more detail, while in flat areas, it reduces the density. It's possible to adjust the density, but to be honest, I understand what it does in practice. Basically, I'm defining the intensity or density of the mesh. Thus, I prefer to use this command because it gives me more control. I usually select by tolerance and set it to 0.1. This means the mesh can be adjusted as long as it stays within a tolerance of 0.1 millimeters. In other words, the maximum error this tool will allow in the mesh is 0.1 millimeters. What this means in practice is that the measurement I took may have an error of up to 0.1 millimeters, either more or less. I'll run the preview. What we expect to happen is that the entire mesh density will be optimized, resulting in areas with large spacings and other areas with more detail where needed. The mesh will eventually become denser in some regions, but nothing like its initial state, making it much lighter overall. And there it is, as you can see. The mesh is clearly dynamic, with higher density in some areas and much lower density in the flat ones. That's precisely what I want. Some regions are a bit messy, probably containing some debris, but we'll accept it as it is. After this operation, the mesh has improved significantly. Previously, it was overly dense. What can we do now? We can check if there are still areas that can be cleaned. I'll use the separate command, select the object, and check if it identifies detached bodies. Indeed, it found quite a few. This is the main body. Everything else consists of small islands separated from the primary object. Some of them are very small. These islands can be safely deleted. I'll select them. Using the right mouse button, I'll choose Remove instead of Delete. Remove logs the operation in the timeline, whereas delete would erase the entire body. The message that appears isn't an error, but rather an alert indicating that the mesh is open. This is expected and doesn't affect our goal here. Now, with the model perfectly aligned and the mesh in an acceptable state, we can proceed to take a new measurement. Using the inspect command, I'll measure again. Rechecking the measurement, the dimension remains at 22.073 millimeters, meaning there's been no change. Now we move to the solid mode to start creating the object. To do so, I'll select Sketch. Notice that the plane is coincident with the base of the piece. From here, we can begin tracing what we consider to be the main object. Simply click on a region, as I'm doing, and manually adjust as necessary. The piece will now be roughly in the correct position. Recalling our earlier measurement, the width is about 22 millimeters. I won't enter 22.084 millimeters, just 22 millimeters, which will establish the foundation for constructing the piece. In this situation, I can also check the total length. Which is about 27 millimeters. I'll dimension this area and set it to 27 millimeters, which is nearly the exact value. If I wanted to apply a fillet, I could do so now, adding it to the corners. The fillet would be 1 millimeter, almost certainly, as it's a logical value used in the object's original design. Here, the object might not be entirely aligned, which explains some of the deviation. However, at the top, the alignment is coincident with the face, but it starts to deviate as we move toward other areas. I've made an alignment of about 0.5 degrees, but it probably should have been less. Here, an interesting situation arises. If we want to create a circle based on 3 points, we can select those 3 points without needing to pinpoint the exact center, which would be challenging. The available tools, such as the 3-point circle, exist for good reasons. Let's check the size of this circle. It measures around 6 millimeters, or more precisely, 5.97 millimeters. We'll adjust it to 6 millimeters and proceed. Next, we'll identify the point at 90 degrees, the first quadrant of the circle. This is simply a verification step to ensure accuracy. Returning to the circle tool this time, we'll use the standard circle, as we now know the center, and that it is concentric. The radius appears to be 2.5 millimeters. We'll test 2.6 millimeters to allow for a slight tolerance, as it will likely accommodate a 2.5 millimeter screw. On the other side, we encounter the same situation. This is the perfect time to use the mirror command to reflect the entities. We select the objects and the symmetry line. Once done, the other side is automatically generated. Now we can view the piece and check if it looks as intended. Everything appears correct. Next, we move on to the extrusion. We activate the piece and, for better visualization, adjust the opacity to about 50%. We close the sketch and apply the extrusion. We select the desired areas and proceed with the extrusion. Setting the value to 1.6 millimeters. We notice that the sketch began slightly below, causing a small issue. We adjust the extrusion to 1.7 millimeters and analyze again. To completely resolve the issue, we could add a value of 0.1 millimeters on the opposite direction of the extrude, but we can go back in the timeline to before the sketch creation and create a parallel plane with an offset. A plane was created with an offset of minus 0.1 millimeters, resulting in a new plane positioned correctly. The sketch was transferred to this new plane, which is slightly below the previous one, allowing for greater precision in modeling. The extrusion was reactivated, and it was observed that the coverage was almost complete, except for a small area. This approach more accurately reflects reality, as slight distortions in the original piece begin to appear. To improve, piece's rotation was corrected by 0.5 degrees. Resulting in a more precise position. The piece was then moved 0.1 millimeters for better alignment. Despite some remaining deviations, the generated solid largely coincided with the initial mesh, demonstrating a good fit. This approach requires attention to detail to ensure the model's accuracy, especially for more complex pieces. After analyzing and adjusting the fillets, it was observed that the digitized piece has slight imperfections but is generally well aligned. Nevertheless, additional refinements could be made to achieve perfection. In the next phase, the modeling process continued with new sketches. This was streamlined by opening a sketch directly in the required area, saving time. This method is common when modeling prismatic or revolved pieces, which use simple geometric elements as a base. For this piece, it's a relatively basic example. In this video, we explored the process of 3D scanning and modeling a simple prismatic piece, starting with high-resolution scanning, optimizing the mesh, and creating an accurate CAD model in Autodesk Fusion. We highlighted key steps like handling reflections, aligning scans, and refining details to achieve the best result. This example laid the groundwork for more advanced applications, and in the next video, we'll tackle a more complex piece with organic geometry. Thank you for watching, and see you in the next one.